We've been discussing how ODEs are used to model problems in classical mechanics, in population dynamics. We also talked about the Newton's law of cooling. And now I want to introduce a new type of problem that can also be modeled with ODEs, mixing problems. Here we will see the power of the conservation principles that we talked about in the introductory videos. As a matter of fact, I strongly recommend that you watch the introductory videos again before diving into this example. It will help remind you of the assumptions that we analyzed there, which are commonly used in modeling with ODEs. Those assumptions will play a key role in this example. So here is a classic example of mixing problems. Let's see what our example says. We have a tank, and at time t equals 0, our tank contains S0 equals 20 pounds of salt dissolved in 100 gallons of water. So that is at time t equals 0. Assume that water containing 0.4 pounds of salt per gallon is entering the tank at a rate of R in. This is the rate at which this salt water is entering the tank, 10 gallons per minute. So another way of saying this is that water with salt concentration of 0.4 pounds per gallon is entering the tank at the rate of 10 gallons per minute. All right, so that is one of our assumptions. And we have the picture on the right. We have our tank, and there is here we have our salt water, the mixture of salt and water. It's entering the tank at the rate of 10 gallons per minute. And also assume that the water is mixed instantaneously, and the well-stirred mixture exits the bottom of the tank at a rate of R out equals 5 gallons per minute. So the water is entering the tank and it is leaving the tank, right? The salt water, the mixture of salt and water. So what is the question? Let S of t be the amount of salt in the tank at time t. For example, it is given to us that at time t equals 0, the amount of salt is 20 pounds. But this is more general. At time t, let's denote the amount of salt in the tank by S of t. Set up an initial value problem. That means the differential equation together with an initial condition for S of t. Of course, the initial condition is given to us, right? The key here is to find the differential equation for S of t. All right. Folks, now let me start by making a couple of observations about the assumptions in this model, and then we'll work on solving the problem together. So first, I wanna carefully go over the assumptions that we are making in this model. Some of them are not actually very obvious. So first, notice that the problem says the water is mixed instantaneously as the solution, as the brine solution is entering the tank. So let me make a comment about that. So here I'm gonna going over the assumptions quickly. We always assume that the brine solution, but by the brine solution, I mean the mixture of salt and water. That is what I mean by the brine solution. Remains perfectly mixed. What that means is that we're not worrying about the idea that the salt concentration might be heavier over here at the bottom, or might be lighter over here at the top, right? We are assuming that the solution remains perfectly mixed everywhere at all times. So to be very clear about this assumption, so for example, for example, when we say at time t equals 0, 20 pounds of salt is dissolved in 100 gallons of water. When we say at t equals 0, 20 pounds, this is L, this is supposed to be my L, 20 pounds of salt is dissolved in 100 gallons of water. We interpret this as the salt concentration being 20 over 100, which is 1/5 pound per gallon. This means that if we take a gallon of water from anywhere in the tank, it will contain exactly 1/5 pound of salt. So let me also clearly write that. This means that if we take a gallon of water at time t equals 0 from anywhere in the tank at t equals 0, because 20 corresponded to the time t equals 0, it will contain exactly 1/5 pound of salt. Awesome. So what I did in this item, I try to explain this assumption a little bit, that we have a well-stirred mixture. And as the water is entering the tank, again, we always assume that the mixture is well stirred, right? In the sense that we can talk about in a meaningful sense, we can talk about the concentration of salt inside our tank with one number at any given moment of time. All right, so that was one comment that I want to make. Another comment that I want to make about our assumptions here. When we say the salt water mixture enters at a rate of R in, here in this example, 10 gallons per minute. We interpret this as follows. And this actually goes back to some of the comments that we made in our introductory videos as well. So after 1 minute, 10 gallons of salt water mixture will have entered the tank. This should like sound reasonable. I don't think anybody will have a question about this. Now let me continue with this sort of reasoning interpretation. After 2 minutes, 20 gallons of salt water mixture will have entered the tank. So I'm sure that nobody will have a question about that. Now, maybe starting with this third statement, you will get a little bit uncomfortable. After half a minute, 30 seconds, 5 gallons of salt water mixture will have entered the tank, right? So this is the way I'm interpreting this rate of entrance of salt water into the tank. When I say that it is 10 gallons per minute, that means that after 30 seconds, I will have 5 gallons of water, of salt water entering the tank. And now comes the interesting part. More generally, after delta t minutes, this delta t can be a number greater than 1, can be a number less than 1. It doesn't need to be a whole number at all. After delta t minutes, 10 times delta t. Look at exactly what we had in the previous statements. For example, after 0.5 minutes, we had 10 times 0.5. 10 times 0.5 is 5. After delta t minutes, 10 times delta t gallons of salt water mixture will have entered the tank. Beautiful. So again, if you're thinking of delta t as delta t being equal to 1, delta t being equal to 2, delta t being equal to 0.5, maybe you don't have much problem with it, but this is not actually what we're doing here. We're not just assuming delta t being 1 or 2 or 3 or 0.5. Here, and again, I recommend you to go back and see the introductory videos where we talked about these situations more carefully. Here, delta t can be any positive number. It can even be infinitesimally small. As a matter of fact, ultimately, we will let delta t go to 0. We will take the limit as delta t go to 0. It can be infinitesimally small. So I want you to notice that this assumption that I'm making, that this delta t in the statement here can be as small as I wish, this is not very obvious. This may not actually correspond to the reality of what is happening, but in order to construct our ODE model, we make this assumption. So let me also write this down. Note that this assumption is not completely obvious. Note that this assumption, note that it may not match what exactly is happening in reality. Note that this assumption that we are making, that this delta t can be as small as we like, and still we will have 10 delta t gallons of water entering the tank of salt water. Note that this assumption is non-obvious. It may not match exactly what we have in reality. For instance, it could happen that during each minute, because it is given to us that each minute 10 gallons of salt water enters the tank, right? But it can happen that during each minute, all 10 gallons of salt water mixture enter the tank only in the last 5 seconds of your minute. Only in the last 5 seconds. Nothing is happening until the 55th second. And then suddenly from the 55th second to the 60th second, when all the 10 gallons of salt water mixture enter the tank. Still, you have 10 gallons of water entering the tank per minute, right? But that is not the assumption that we're making here. We're assuming that this entrance of the salt water into the tank is happening continuously and at a uniform rate. And for this reason, we can assume that as delta T goes to zero, still 10 delta T gallons of salt water mixture is entering the tank. So this is the assumption. So this we are assuming that this situation that I just wrote does not happen. We are assuming that everything is happening continuously at a uniform rate. So, however, in this model, we are assuming that the flow of the salt water mixture, the brine solution, into the tank is both continuous in time and occurs at a uniform rate. And that is exactly why this statement, the highlighted statement, should make sense because of this assumption that we are making. Let me make one more comment here, and then together we will start actually deriving the ODE. So I'm just talking about the assumptions that we are making in this model. Another thing that I want to point out is as follows. I want to talk a little bit about this term volume when we talk about, for example, 10 gallons of salt water mixture or 10 gallons of water. So I want to point out that when we talk about volume here in this problem, we are not making a distinction between volume of water and volume of salt water. It's as if we are assuming that in this context, the contribution of the salt to the overall volume is negligible. We're not making a distinction between volume of water and volume of salt water. For example, in this context, the following two statements mean the exact same thing. The following two statements are the same for us, mean the same thing. So what are the statements? One, every minute, 10 gallons of water, I just said water, enters the tank. Each gallon contains 0.4 pounds of salt. This is exactly the same as saying that every minute 10 gallons of salt water mixture enters the tank, and each gallon contains 0.4 pounds of salt. So again, so in this example, in this model, the contribution of the salt to the volume is negligible. Keep that in mind as well. So very, very good. I think we just very carefully we went over some of the assumptions that we are making in this model. And now let's start thinking about the derivation of an ODE, of a differential equation that governs the amount of salt in the tank at any given time t. That was the question that was asked of us. Find the ODE that governs S of t. S is the amount of salt in the tank at time t. And as we will see in a second, we will use a conservation principle in order to derive our ODE. So let me write that. Our derivation of a differential equation governing S of t, the amount of salt in the tank at time t in pounds, will rely on a straightforward conservation principle, which we discussed in our introductory videos. So what is the conservation principle? And again, I recommend that everybody goes back to the introductory videos where we carefully talked about conservation principles. So, and it should make sense. As I'm writing it, it should make perfect sense, the equality that I'm gonna write. The change in the amount of salt in the tank over the time interval from t to t plus delta t, this equals, let me use a different color, the amount of salt entering the tank during that interval from t to t plus delta t minus the amount of salt leaving the tank during the same interval from t to t plus delta t. This is our conservation principle, right? I'm gonna give a name to this. I'm gonna call it a star. I will refer back to this conservation principle. I'm gonna call this a star. All right. So this should make perfect sense, right? Of course, if you again look at go back to our introductory videos, you will see that we had another version of conservation principles as well. It is possible here to start with the rate of change version of the conservation principle. I could have done that. We discussed the rate of change version of the conservation principle in our introductory videos as well. But that would be like taking a shortcut. If I do that, some of the nuances, some of the implicit assumptions involved in deriving the ODE here would get brushed aside. So I don't want to do that. I want you to see all the assumptions that are being made clearly. So I'm not going to use the rate of change version of the conservation principle. Now, I noticed that many of the resources out there, when they want to solve these problems, they use the rate of change version, the rate of change version of the conservation principle, which is okay. But I think when we start like this, we'll be more careful about the assumptions that we are making in order to derive our ODE, as you will see. All right. So now we have three quantities here that we want to study. Let me give a name to these quantities. So this is what we have on the left. I'm gonna call this one. This is quantity one, and then this guy two, and this guy three. I wanna express them using mathematical notation. Starting with one is the easiest to understand. So the change in the amount of salt in the tank over the time interval from t to t plus delta t. So what is that change? At the time t plus delta t, the amount of salt is s of t plus delta t. At the time t, the amount of salt is S at t. So the change is S of t plus delta t minus S of t. This is the change in the amount of salt in the tank from t to t plus delta t. So that one was very easy to express using our mathematical expressions and notation. Now let's focus on two, the amount of salt entering the tank during that interval, the interval from t to t plus delta t. Now I want to focus on two. Or so let's see what we know. We know two things. Let me call one of them one of them two. One is that over the time interval from t to t plus delta t, as we just discussed. And delta t can be very small. Again, going back to the discussions that we had a few minutes ago, R in times delta t gallons of salt water mixture enters the tank. This is the gallons of water entering the tank. And again, remember, I can use water or salt water mixture. It doesn't make a difference in this context. And then two, now, each gallon, what do I know about the amount of salt in each gallon? Each gallon, the statement of the problem tells me that each gallon of our salt water mixture that is entering the tank contains 0.4 pounds of salt. So when you put these two together, one and two together, what do they tell us? The amount of salt entering the tank during this interval, during the interval from t to t plus delta t, is 0.4 R in times delta t. Of course, R in is also given to us. I'm gonna use R in, but the value of R in is also given to us in the statement of the problem. So just going over this again, during delta t units of time, R in delta t gallons of water is entering the tank. Each gallon has 0.4 pounds of salt. So the total amount of salts entering the tank in this interval is 0.4 R in delta t. That is like now we found the formula for this two, the second expression. So let me actually call this double star. So we had a star our conservation law. This conclusion I'm gonna call double star. And later we will use double star and star. And now let me focus on 3, the amount of salt that is leaving the tank during this interval. So again, I'm gonna write the things that I know. 1, I know that over the time interval from t to t plus delta t, R out delta t gallons of water or salt water mixture leaves the tank. No matter how small delta t is, as we discussed, because of the way we are thinking about how water is entering the tank, how water is leaving the tank, everything is continuous in time, happening continuously in time at a uniform rate. Now, this statement is correct. All right, so far so good. And then 2, now, so now I need to know about the concentration of salt. This water is exiting the tank. What is the concentration of how much salt do I have in each gallon of water that is exiting the tank? That is what I'm interested in. And for that, I need to know the concentration of salt inside the tank. I'm gonna use the fact that we assume that the mixture is well stirred. So that is how I'm gonna figure out what the concentration of salt is inside the tank, and then that will help me in calculating this quantity 3 that I want to calculate. At time t, the concentration of salt in the tank is given by, okay, how much salt do we have inside the tank at time t? That is S of t. How much water do we have inside the tank at time t? So let's do volume of water. And again, remember, in this context, where the salt is not, the contribution of salt to the volume is negligible. That is why I write volume of water in the tank. At time t. It doesn't matter whether I write volume of water or volume of salt water. We are considering them to be the same at time t. So this is equal to S of t. At time 0, what was the volume of water inside the tank? 100. Each minute, we have R in gallons of water entering the tank, and we have R out gallons of water exiting the tank, leaving the tank. So after t units of time, we have R in minus R out t change in the volume of water, right? So after t minutes, we have R in times t gallons of water entering the tank. They have entered the tank. R out t gallons of water left the tank. So the change in the volume of water will be R in minus R out times t. Now, in our example, if I'm remembering it correctly, I think R in is greater than R out. But this formula works in any case, right? Now, let me actually scroll up, remind myself what R in was, what R out was. In our example, R in is 10, R out is 5, so the volume is increasing, but water inside the tank is increasing. But the way I wrote things, it will work even if R in is less than R out. In that case, the volume of water is decreasing as T increases. All right, so this is the concentration at time T. And of course, as you can see, it changes with T. This concentration changes with T. Now, And now let's focus on another assumption that we're making. And again, these are the things that we also discuss in our introductory videos. Assuming delta t is very small, my friends, ultimately I'm gonna take the limit as delta t goes to 0 to arrive at a differential equation, an equation that involves the derivative of s of t. So ultimately the goal is to take the limit as delta t goes to 0. So this is not like a weird assumption to make that assume that delta t is small. Assuming delta t is very small, eventually we will take the limit. Eventually we will take the limit as delta t goes to 0. We will take the limit as delta t goes to 0. We can assume, we can write, we have concentration of salt in the tank during the very small interval from t to t plus delta t. I know that this concentration is changing. In reality, it depends on t. It's not one number in this interval, but since I'm assuming that interval is very, very small, I can say that the concentration at any time during this interval is approximately equal to the concentration of salt in the tank at time t. And again, this is something that we discussed in the introductory video. When you have a continuous function over a very small interval, you can approximate the value of that continuous function with a constant number. What the value of that continuous function is at the left end point of the interval. And this is exactly what we had above. This is s of t divided by 100 plus r in minus r out t. This approximation becomes better and better, becomes more accurate as delta t goes to 0. So putting all of these things together, so let me actually rewrite the main conclusions here. So these are the things that we have. And now I can easily determine the amount of salt that leaves the tank. So as a matter of rewriting, so therefore to sum up, let me rewrite the things that we discovered over the time interval from t to t plus delta t, r out delta t gallons of salt water mixture. This is just, I'm rewriting one item, one above, a mixture leaves the tank. This was one of our discoveries. Leaves the tank. And then we also discovered that over this interval, over the time interval from t to t plus delta t, each gallon of salt water mixture contains approximately, and this approximation becomes more accurate as delta t goes to 0, s of t divided by 100 plus r in minus r out t pounds of salt. So putting these two together, now we know the amount of salt that leaves the tank. The amount of salt leaving the tank during the time interval from t to t plus delta t is approximately, and this approximation becomes better and better, more accurate as delta t goes to 0, S of t divided by 100 plus R in minus R out delta t, I'm sorry, times R out delta t. So the gallons of water that leaves the tank here, and each gallon of water contains this amount of salt. So this is the total amount of salt in pounds leaving the tank during this interval. So this approximation becomes more accurate as delta t goes to 0. Let me call this triple star. So let me scroll up and let's do a review of what we have done. So we had this equality star here. And then what we did, we computed the left-hand side. We have a formula for the left-hand side. And then double star gives us a formula for the first term on the right-hand side. Triple star gives us a formula for the second term on the right-hand side. So putting all of these things together, we will have, therefore, a star, double star, triple star, they tell us that S of t plus delta t minus S of t is approximate, and this approximation becomes more accurate, becomes better and better as delta t goes to 0. 0.4, this is the double star, R in delta t minus, and then triple star, S of t divided by 100 plus R in minus R out times t, and then times R out delta t. And we know that this approximation becomes better and better as delta t goes to 0. This approximation becomes more accurate as delta t goes to 0. And that is exactly what I want to do. I want to take the limit as delta t goes to 0 because I want to arrive at an equation that involves derivatives. So immediately from this, we divide both sides by delta t. (0.4) R in minus, I divided both sides by delta t, 100 plus R in minus R out. And again, remember, R in and R out, they are numbers that are given to us in the statement of the problem. R out. And now I'm going to take the limit as delta t goes to 0 by taking the limit as delta t goes to 0. Well, of course, 0 plus from the right. The delta t is not negative. We obtain. So the left-hand side, when you take the limit as delta t goes to 0, that is the derivative. And then the right-hand side doesn't have any delta t in it. And remember, as delta t goes to 0, our approximation becomes accurate. So 0.4 R in minus S of t divided by 100 plus R in minus R out t times R out. This is the differential equation that S of t must satisfy. Of course, in this example, the values of R in and R out are given to us. So the rest, I'm gonna just substitute those values. Substituting R in equals 10, R out equals 5. We get, so what will happen if R in is 10, R out is 5, ds dt will be equal to 4 minus R out is 5, so I have 5 s of t in the numerator, and then the denominator R in minus R out is 10 minus 5, which is 5. That will be 100 plus 5t. And of course, I can actually factor out 5 in the right-hand side. It's unnecessary to do it, but you can. We have 4 minus 5 s of t, and then I can factor out 5 in the denominator, 20 plus t. 5 and 5 will cancel. So that tells me that ds dt is equal to 4 minus s divided by t plus 20. This is our differential equation, a linear first order differential equation, or equivalently ds dt plus 1 over t plus 20. S is equal to 4, a first order linear ODE, a linear first order ODE, a linear, you know how to solve it. There is like a standard procedure for solving linear first order ODEs using integrating factors and so on and so forth. A linear first order ODE. Of course, the purpose here is not to solve it. We just wanted to find the governing equation. So what is our initial value problem? Our initial value problem is ds dt plus 1 over t plus 20s equals 4. S at 0, it was given to us, it is 20 pounds. 20 pounds. We did it. We did it. We carefully went over all the assumptions. I think it's very helpful if you, as you're watching this video, also review what we covered in the introductory videos that we had about modeling with ODEs.